Welcome to Lakshman Reddy Institute of Technology and Management. We are in lecture series of signals and systems in unit 3. In lecture 3, we'll be seeing properties of LTI system. So what are all the properties of LTI system? Before discussing that, we shall see why this impulse response is very important for LTI system to be understood. So an important representation of continuous time LTI system is in terms of its unit impulse response. So unit impulse response is nothing but h of t. So h of t is very important because it is used to understand the characteristics of an LTI system completely. Okay, so by using impulse response we can find the characteristics of an LTI system completely. The unit impulse response of a non-linear system does not completely characterize the behavior of the system, which means if the system is non-linear, okay, non-linear means we know the property, right? So if weighted sum of inputs are equals to weighted sum of outputs, then it is called as linear system. If a system is non-linear, then it does not completely characterize the behavior of the system. So let us see some properties, very important properties of LTI system, linear LTI system. Okay, so linear means obviously LTI means linear time invariant system. So that's why we'll be seeing only for linear systems. The commutative property. What is commutative property? If you multiply in any direction, it will be getting the same answer. So that is in maths. So in general, in the same way, in signals also, if you do convolution of two different signals or one signal x of t and impulse response h of t, or if you do convolution in reverse way, that is h of t convolution x of t, both gives the same answer. So that is commutative property. Integral minus infinity to infinity. What is convolution formula? Expand convolution formula. Integral minus infinity to infinity. One signal as it is x of tau and another signal shifted by t units. After flipping, you should shift the signal by t units. H of t minus tau d tau. Or in reverse way, for h of t convolution x of t, this one. So we can write like integral minus infinity to infinity h of tau into x of t minus tau d tau. That is the output of an LTI system with input x of t and impulse, unit impulse response h of t is identical to the output of an LTI system with input h of t and impulse response x of t. Then we'll go to second property, that is distributive property. We all know the distributive property also. A into b plus c equals to a into b plus a into c. In the same way, signals also, x of t convolution h of t plus h1 of t plus h2 of t gives x of t convolution h1 of t plus x of t convolution h2 of t. So this is distributive property. So in graphical representation, we can show like this: x of t and h1 of t are convolving each other, okay, and x of t and h2 of t are convolving. So when you add up, you will be getting y of t equals to x of t into h1 of t plus x of t into h2 of t here at this point, which is same as x of t with the system combinedly h1 of t plus h2 of t gives y of t. So this is distributive property. Then coming to associative property. Associative property, we all know in maths, like a into b into c equals to a into b into c. So here B and C will be in brackets in LHS, and in RHS A and B will be in brackets. So similarly, x of t convolution h1 of t convolution h2 of t gives x of t convolution h1 of t first, and then if you do convolution of h2 of t, both the same answers will be same. RHS and LHS answers will be same. Okay, so that in graphical representation is like this: x of t convolution h1 of t, and if you do convolution of h2 of t, you will be getting y of t. Whereas x of t convolution with h1 of t and h2 of t convolution, you will be giving as output y of t. So both will be same. Similarly, next property is systems with and without memory. We have already seen what is static system and dynamic system. Static system is without memory, and dynamic system is with memory. So the same we shall see once again. A system is said to be static or memoryless if its output at any time depends only on the value of the input at that time. So what does that mean? So if the output is depending on only present inputs, then it is static, or else it will be dynamic. If it is depending on past or future inputs, then it is called dynamic system. So a continuous time LTI system is memoryless if h of t equals to 0 for t not equals to 0, and such a memoryless LTI system has the form, we can represent it as y of t equals to k into x of t, where k is some constant has the impulse response. Okay, so impulse response can be written as h of t equals to k into del of t. So what is del of t? Impulse signal. So when you multiply del of t with some constant k, if you are getting h of t, and h of t is not equals to 0 for t not equals to 0. That means if you are taking present inputs, okay, you will be getting only present output. Okay, the present output is depending on only present input. Such kind of system are static or memoryless. Okay, and the continuous system has memory. Okay, a memory system is also called dynamic system. We have already seen the system which is having memory or which is depending on previous inputs and future inputs, that is called dynamic system. If k equals to 1, h of t equals to del of t. So this kind of system is known as identity system. Okay, such kind of system is known as identity system. Next, causality. We have already seen what is causal rate. So which is the condition? Causality means, so integral over the impulse response over finite impulse response should be less than infinity, or it should be a finite value. We should not get infinity as the answer. So such kind of systems are causal systems. So a causal system is non-anticipatory and does not produce an output before an input is applied. So output we should not get before the input is applied. All real systems are causal systems, because before giving input we will be not getting the output. So its output depends only on the present and past values. Okay, past inputs and present inputs, it will be depending on the present output will be depending on present and past inputs, but not on the future inputs. Such kind of systems are causal systems. So for a causal LTI system, we have h of t equals to 0 for t less than 0. Okay, output of causal LTI system for a non-causal input, if it is non-causal input, that is x of t is varying from minus infinity to infinity. Okay, so if you take x of h of tau into x of t minus tau, x of t minus tau is from minus infinity to infinity, which is applied to a causal system. Causal system means h of tau is from 0 to infinity, minus infinity to infinity, and 0 to infinity common area will be 0 to infinity. Therefore the limits also will be from 0 to infinity. And in other way, if you write, so x of tau into h of t minus tau, the input signal as it is and impulse response shifted, flipped and shifted. So x of tau is varying from minus infinity to infinity, h of t minus tau is flipped means minus infinity to 0 and shifted to t, therefore minus infinity to t, the common area will be minus infinity to t. Okay, so this is non-causal input. So output of a causal LTI system for a causal signal. So if it is causal signal, x of t is from 0 to infinity. Causal system is means 0 to infinity, common area will be 0 to t. If you write anyways, either h of tau into x of t minus tau d tau, or in reverse x of tau into h of t minus tau d tau, both will be same limits, 0 to t, because the input signal is causal, that means 0 to infinity. The system is also causal, 0 to infinity, but you are flipping the signal, one signal, and flipping means it will be coming from minus infinity to 0 and it is shifted by t units, so you will be getting till t. So what is the common area between all these is only 0 to t, so that's why we are getting the limits 0 to t. And a non-causal system. So what is non-causal system? Okay, so it depends on future inputs. Okay, it is an anticipatory system. So h of t will not be equal to 0, it will have some value for t less than 0. So such kind of systems are non-causal systems. So h of t, impulse response, will have value for t less than 0. Such kind of systems are non-causal systems. Okay, then coming to stability, we have already seen this stability condition: bounded input, bounded output. So bounded input, bounded output means integral minus infinity to infinity modulus of h of tau d tau should be less than infinity. The value should be finite, then only we can say the given system is stable. If it is infinite, then it is unstable. So I repeat, causal means you need to check whether it is depending on only present and past inputs. If it is depending on future inputs, then it is non-causal. Linear means it should be depending on the condition, it should be obeying the condition. Weighted sum of inputs should be equals to weighted sum of outputs. Time invariant means time invariant is something like it should not be, when input is delayed by capital T units, output also should be delayed by capital T units. If not, it is time variant. Then static means it should be, the output should be depending on present input only. The present output should be depending on present input only, but not on any past inputs or future inputs. So stability condition is this. So bounded input, bounded output should be there. If the input is bounded, that means you are giving a finite input, your output also should be finite. To prove that, we need to take integral minus infinity to infinity modulus of h of tau d tau and do the answer. If it is a finite value less than infinity, then it is said to be stable or else unstable. Next, invertibility. We have already seen this invertibility. So So if you are giving input x of t for a system h of t, and if you are getting y of t as the answer, and if you give y of t to another system h1 of t to obtain x of t back, the input x of t is able to get at the output after transforming twice, then it is called as invertible system. Okay, so if you are not getting this x of t back, then it is non-invertible system. Okay, so impulse response h of t convolution with another impulse response h1 of t, if you are able to get del of t, then such kind of systems are invertible systems. Okay, x of t, if x of t is the input to identity system del of t, then you will be getting x of t back. So this is about invertible systems. Okay, so it is any system which can be known as invertible if an inverse system with impulse response h1 of t, which when connected in series with the original system produces an output equal to the input of the first system. Okay, so if this is the second system h1 of t, if this is the first system h of t, so if h1 of t output is h of t's input, okay, that is first system's input, then it is invertible. Okay, so unit step response. So step response is denoted by s of t. We all know that step response means the input should be u of t. So h of t convolution u of t is nothing but step response. So you can reverse it, u of t convolution h of t, and the answer will be integral s of t equals to integral minus infinity to infinity h of tau d tau, because u of t or u of t minus tau will be 1 for within the limits we get. Okay, the unit step response of continuous time LTI system is nothing but a running integral of its impulse response. So here we have already seen in first unit, like the step signal, if you differentiate, we will be getting impulse signal. So in the same way, if you differentiate step response d by dt of s of t, you will be getting impulse response, which is h of t. So I repeat, as we have seen, differentiation of unit step signal gives unit impulse signal. In the same way, differentiation of unit step response gives unit impulse response. Okay, very important. That's all about today's session. If any questions, mail me at kvskumar29 at mlradm.ac.in. Thank you.